It's an honor to be able to address you virtually as part of this conference honoring the life and contributions of Hungarian-American scientist John von Neumann. My name is Robert Baker. I'm a professor of chemistry and biochemistry at The Ohio State University. I'm also a recipient of the John von Neumann Distinguished Fulbright Fellowship, which supported my recent research collaboration with the Extreme Light Infrastructure attosecond light pulse source in Szeged, Hungary. In this talk, I would like to describe a few of von Neumann's seminal contributions to the fields of chemistry, physics, and molecular spectroscopy, and to provide a brief highlight of my Fulbright Fellowship in Hungary. One of von Neumann's most important contributions to the field of chemistry was the development of group theory. Group theory is the algebraic formalism that categorizes objects within groups based on existence of similar symmetry elements. Group theory can be used to describe a number of physical systems, including crystal lattices, electronic orbitals and atoms, and molecular symmetries. Group theory has become absolutely fundamental to using symmetry to predict the way that light interacts with matter. In this sense, group theory provides a foundation for using spectroscopic measurements of light to determine molecular structure and dynamics. Here are shown a few textbooks on group theory that are in the library of almost any inorganic or physical chemistry graduate student. Of course, one of von Neumann's most important contributions to chemistry and physics is a mathematical description of quantum mechanics. Time-dependent quantum mechanics describes the dynamics of molecular systems, including electron motion. Although his landmark publication, Mathematical Foundations of Quantum Mechanics, was published in 1932, over 90 years ago, the ability to experimentally probe some of the basic predictions of quantum mechanics, such as coherent wave packet motion of electrons, is only recently able to be observed, as shown on the lower right of this slide, where attosecond pulses of light enable real-time observation of valence electron motion in krypton ions. The importance of being able to measure electron motion was recognized just last month with the 2023 Nobel Prize in Physics awarded to Pierre Agostini, Ferenc Krauss, and Anne Louier for the creation of pulses of light with extremely short attosecond durations. I received my own scientific training from the Hungarian-American scientist Gabor Somerjai. I earned my PhD in 2012 at the University of California, Berkeley, working under the direction of Somerjai. Notably, in addition to being a pioneer of modern surface science, Somerjai was also a participant in the Hungarian Revolution of 1956, before he immigrated to the United States with his wife, Judy. One of the primary findings for my work with Gabor Somerjai was the discovery that acid-base catalysis on surfaces explains the molecular origin of strong metal support interactions and heterogeneous catalysis. Acid catalysis is a field that was strongly influenced by Hungarian-American scientist George Olah, who was awarded the 1995 Nobel Prize for his contributions to understanding superacid catalysis. This is a field that today is responsible for an incredible number of industrially important chemical transformations. Importantly, these reactions that are catalyzed by superacids proceed through charged intermediates, such as the carbocation shown here. Because these charged species are highly reactive, they exist for only a very short lifetime, making them difficult to study. The ability to directly observe such short-lived species involved in important chemical processes is what inspired me to pursue postdoctoral training in time-resolved spectroscopy following my PhD with Gabor Somerjai. I received this training from Stephen Leone, also at University of California, Berkeley. It's here that I learned how the process of high harmonic generation is able to produce pulses of light with durations as short as attoseconds. 1 attosecond is 10 to the minus 18 seconds. In other words, there are more attoseconds in 1 second than there are seconds in the estimated age of the universe. It is this level of precision that ultimately allows scientists to directly observe electron motion as it sets into course important chemical and energy conversion reactions. Understanding these processes has been the focus of my research group at The Ohio State University since 2014. In 2023, I was privileged to receive the John von Neumann Distinguished Award in STEM from the U.S. Fulbright Scholars Program, with strong support from Fulbright Hungary. Pictured here are two of my Hungarian hosts for this project, Dr. Katalin Barju, Scientific Director of the Extreme Light Infrastructure Attosecond Light Pulse Source, and Dr. Peter Domby, Head of the Ultrafast Science Application Divisions at this facility. The Extreme Light Infrastructure Attosecond Light Pulse Source, or ELI Alps, is located in Szeged, Hungary. It is part of the larger ELI European Research Infrastructure Consortium. This facility opens the door to new frontiers in chemistry and physics by providing access to light sources capable of observing ultrafast attosecond and femtosecond processes. While at ELI Alps, my student Emily Hruska and I had the opportunity to work with the high repetition rate attosources group shown here toward the development of ultrafast X-ray transient absorption of solids at extremely high 100 kilohertz repetition rates. My research group continues to benefit from ongoing interactions with the research scientists at ELI Alps. As shown here, my student Harshad Gajapathy is working with the ELI Alps surface dynamics team to study charge and spin resolve transport using their Nano ESCA instrument. As was recently highlighted in this report by the U.S. National Academy of Science titled Reaching for the Brightest Light, the ELI project is providing inspiration for similar endeavors in the United States around high-intensity ultrafast lasers. With inspiration from the ELI project, I am leading a team of researchers at The Ohio State University to construct a high-power ultrafast laser facility titled the National Extreme Ultrafast Science Facility, or NEXUS. This exciting project is sponsored by the U.S. National Science Foundation. These highly synergistic efforts taking place in the U.S. and Hungary provide exciting opportunities for future collaborations between research communities in these countries. In particular, I highlight the X-Lights project, which is sponsored by the International Office of the U.S. National Science Foundation. This project is supporting activities designed to accelerate networking between international researchers sharing common interests in extreme light across North America, Europe, and Asia. I would like to close by again emphasizing the transformative impact that von Neumann has had on shaping the fields involved in these ongoing research efforts, as well as thank the Hungarian Fulbright Office and my collaborators and colleagues at ELI Alps who have enabled this very rewarding experience. And thank you very much for your time and attention.